more receptors to be made and inserted into the cell membrane. And again, you don't need to know, it will cause more funny channels to be made. You don't need to know these specifics. 3 years, I'll make them learn them. Okay, right now I'm just adding it up there as a kind of an interest of how that works. So thyroid hormone increases heart rate, and it makes sense if you think of the increased metabolic drive the thyroid hormone produces. Estrogen decreases heart rate. So if a woman is in menopause and has lowered estrogen levels, as she gets older, you're going to see increased heart rate. And ERT, estrogen replacement therapy, is lauded because of it's interesting, it's lauded because of the positive effects it has on the heart, and yet for some individuals can cause blood clots. So it has some of these opposing effects. Again, this is just for interest's sake on how it does that. 11 o'clock last night, I was having a hard time reading the papers, the research papers on that, so I kind of cortisol is thought to increase heart rate because of the stress, also sympathetic. So things that reduce cortisol release are also stressful structures, so it's hard to separate what is actually a cortisol cause and what is a sympathetic cause. But for those three hormones, thyroid and cortisol are going to increase heart rate, estrogen is going to lower heart rate. And that's about what it, as far as you need to know the details for that. I just find it easier to remember if I understand how it works. For the ion effects, I'm going to look at just one. We were doing the death by poison. There'll be another short discussion of this. These are the changes in the ECG as increases in blood levels of potassium occur. So at first, just normal is 3.5 to 5 milliequivalents with a slide 7, you see a peaked T wave instead of the rounded one. That deal is dealing with contractile cells, so for most of what I have written here, I'll come back to it. But you can see here, this is still the contractile cell, and hyperkalemia doesn't seem to have as much an effect on the SA node, so it seems to be immune to it, but it does make the cells more irritable. So at low levels, they're more likely to contract at a faster rate, so you can get arrhythmias. Not necessarily a faster heart rate, but arrhythmias. So when we come back and talk about stroke volume and contractility, we'll come back and look at its effect on the contractile cells in that fashion. So we'll come back to these slides in just a moment. Okay, so the other half of our equation for cardiac output, remember right now we're just looking at cardiac output, not peripheral resistance. The other half of our equation was stroke volume. So what do we mean by stroke volume? What affects stroke volume? How hard the ventricles are squeezing. All right? So heart rate has to do with the autorhythmic cells, as I wrote up on the board earlier. Stroke volume has to do with the ventricular contractile cells. What's the primary ion involved in ventricular contractile cells as far as force of contraction? Whether we're talking about skeletal muscle cell or heart muscle cell? Calcium. Again, because calcium, as we increase intracellular levels of calcium, we get more binding sites for myosin and actin. It's like adding more people on to the end of a tug-of-war rope, and that creates more tugging, more pulling, more force. There are two ways of affecting that contractile force. The first one here is the sympathetic nervous system. Notice I do not have parasympathetic up there because we do not have significant number of receptors for acetylcholine on the ventricular contractile cells. We can increase the force of the atrial contraction, but that's not really relevant to stroke volume significantly. I'm looking for, let me go back to another slide here. slide when we looked at our contractile cells. And notice we have calcium stored in the sarcoplasmic reticulum. We also have a greater amount of calcium coming in from extracellular areas. So the effect of the sympathetic nervous system on contractile cells, so we have norepinephrine binding to its receptor, G protein activating adenylate cyclase, ATP being converted to cyclic AMP, and cyclic AMP is going to open those long-lasting calcium channels in the plasma membrane. So we're going to get calcium from outside the cell because cyclic AMP is binding here. In addition, cyclic AMP activates our phosphorylating enzymes known as protein kinase. Remember protein kinase? Protein kinase is going to go to the sarcoplasmic reticulum and add phosphate groups to calcium channels in the sarcoplasmic reticulum. And we also get calcium from inside the cell. So through these two mechanisms, sympathetic nervous system can activate calcium from the sarcoplasmic reticulum and from outside the cell. Extra calcium means more binding sites. So what is the effect of a calcium blocker, a calcium channel blocker?
Lower the blood pressure.
It's going to decrease blood pressure, okay, because it's going to decrease the contractility of the ventricular contraction. So the volume will be less that's being put out into the blood vessels. So major role of the sympathetic nervous system then is affecting calcium components, content, if you will, of contractile cells. So that brings us then to the second factor that affects stroke volume. And this falls under a term, I'm not sure if you've heard of it before, of Starling's law. So, my fist here is the ventricle. The rubber band is in reference to the myocardium of a ventricle. So what's important here is the recoil component of the muscle, not just the elasticity. So as blood flows into the ventricle, the ventricular wall expands. And then what Starling's law says is the greater the degree of stretching of those myofibers, the greater the force with which they will contract.
This is true.
So if we stretch it out and it contracts with the same force, then we're just going to do this. To come back to its original shape, it has to contract harder. Okay? So Starling's law says if we stretch it a lot, it contracts a lot. If we stretch it a little, it only contracts a little. And we can keep up with the venous return. So venous return is that volume of blood that is coming from the superior vena cava and inferior vena cava primarily into the right atrium. The more venous return there is, the greater the volume the ventricles are stretched to. The greater the volume the ventricles are stretched to, the greater the force of their contraction. So what factors affect venous return? Do you remember the term end-diastolic volume? We looked at it when we drew the diagram of the cardiac cycle. Whoops.
Sorry about that.
Thank you. So during ventricular filling, the very bottom of your cardiac cycle diagram, we had the ventricles filling with blood. And then it reached a straight line. where it was level, and we called that end diastolic volume. The beginning of this flat line was our iso, or that extent of time is our isovolumetric contraction period. So what valves have to close for that to begin? What valves are open to allow the ventricles to fill with blood? The AV valves. Semilunar valves are already closed. So at the beginning of end diastolic volume, AV valves close. Semilunar valves are closed. At the end of isovolumetric contraction, AV valves remain closed. Semilunar valves open, and we begin ventricular ejection. So we're ejecting blood into the aorta. So what happens to ventricular volume?
It drops
It's going to drop,
until it hits the end of the systolic.
and it's going to become level as soon as the semilunar valves close again. Which makes sense, because now no more blood is leaving. So now we have the AV valves remain closed, and semilunar valves close. And that lasts until the ventricle relaxation allows their pressure to drop below atrial pressure. And then at the end of isovolumetric relaxation, AV valves open. And we begin to fill the ventricles with blood again. So this lowest volume is identified as end systolic volume. So end diastolic volume is the greatest volume, the maximum volume in the heart, and end systolic volume is the lowest. Is it 0?
No.
No.
It never empties all out.
So if we look at this next graph, the heart is expanding due to venous return, and the average end diastolic volume with our 70 beats per minute is 135 mils. We lose slightly more than half of that during ventricular ejection. That leaves us with about 65 mils. Why not go to 10? Why not pump all but 10 or 15 mils out? What is the advantage of only pumping about half?
But the atrium's not as much as the ventricle, so when it's bringing blood in, when it's not stretching out.
Yeah, but it's a little bit more functional than that. If I pumped all but 10 mils of blood out of my ventricles, and then I had a need for a greater volume of blood, I would have no reserve. So this provides a reserve so that if I have to start running, all right, if I need a greater volume of blood, I need to start moving blood through the body faster, more of it to carry more oxygen, I have that reserve. So now my stroke volume increases. Notice what happens to my end systolic volume. It also decreases. Here I've increased end diastolic volume. By doing so, I've increased venous return. So venous return is almost synonymous with end diastolic volume. Venous return is just basically the amount of the blood returning to the heart. If more blood returns to the heart, end diastolic volume is higher. If less blood returns to the heart, end diastolic volume of blood is lower. It's not quite the same definition, but they're directly related. And here are some ways in which venous return can be affected. slow heart rate. Why slow heart rate? Without changing anything else, all I have to do is slow down my heart rate. So if I look at my ECG, what's happening in my TP interval? What do we call that in the cardiac cycle? The period of ventricular filling.
So it gives more filling time.
So, exactly. So if I slow my heart rate down,
You have more time to feel for just in
Maybe
case.
it's less more blood in.
more time for the blood to flow into the ventricle. So fortunately, Starling's law works. So I have a greater volume of blood, greater contraction. Alright? Now, this is what I want to look at tomorrow when we do part of that review. So on this sample exam and part of the review exercise for